This is Lecture 6D for Calculus 2. It is an introduction to work problems. There's a whole description and vocabulary of work. Some of it we just go right by. The first point is that force and displacement are vectors. So work is a dot product between the force and displacement. And so that's written right here. Of course, from trig, you're familiar with dot products. So force dot displacement will be the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. Well, for this class, and many times, this angle between force and displacement is 0. So if theta equals 0, that means the force and the displacement vector are lined up. Cosine theta is 1, and then we have the familiar definition that work is force times displacement, but it really isn't. It's really the dot product. Next point I want to make is that force is the time rate of change of momentum. We're used to just writing force equals mass times acceleration, but that's not the whole story. And now this fourth point is why we need calculus to compute work, and that's because force can change with time and with distance along the displacement, and that's why we need calculus. And I want to make a fifth point here that's going to show up, and that is work problems require paying attention to units. In fact, there's two sets of units. One is the British or imperial units, the other is your MKS, SI, or maybe even your CGS units, and you have to be very careful what set of units you're working with. I'm going to just work through this small little derivative problem that force is the time rate of change of momentum. Momentum is written with a P, of course, and momentum is mass times velocity. So force is the time rate of change, d by dt, of mass times velocity. These two terms are multiplied together. So to take this derivative, we have to use the product rule. The product rule says hold m constant, take the derivative of v with respect to t, then hold v constant, take the derivative of mass with respect to time. Well, the derivative of velocity with respect to time is acceleration, so we have the first term that we're very familiar with. There's also the second term, which is velocity times the time rate of change of mass. In many circumstances, the mass is not changing with time, so this last term is 0. And for the problems we do here, that's how it's going to be. The mass will not be changing with time, and we will be writing force equals mass times acceleration, but for completeness I want to point this out. The classic example that's given for the use of calculus to compute work is the example of the spring. And here's the idea with the spring. Let's say this is 3 snapshots of the spring, and if the resting position of the spring is, say, somewhere like this, the idea is that to stretch it this far requires a force this size, but to stretch it further requires a bigger force. In other words, the more you pull it, the harder you have to pull. And this is written as force equals some constant times x being the distance that you've pulled it off its equilibrium or resting position. K is a spring constant, and it depends on the spring. If you're working with one of those big leaf springs under a truck, K is pretty big. But if you're working with the little spring on the end of your eyeglasses, then K is very, very small. So we just treat K as a constant. Now, if you want to compute the work along here, you would do the typical calculus thing of dividing this into little sections and adding up the work in every section. I'm going to spare you that pain and just go right to the definite integral. So you can see that if you took the limit, it would turn into a definite integral. I think that's pretty obvious by now. So here's work, and it equals the integral over the displacement. In this case, for the spring, it starts at 0 because that's its resting position, and you pull it out to some length d from its resting position. Right? So you're integrating the force times the displacement over dx. Right? And that's your integral. It's really work equals the integral from first position to final position of interest of the force times dx. And force can vary with position, and it does here because force is k times x. So, of course, you can carry out the power rule and solve this, and there's the answer, and that will give you the work. So here's this expression we wrote on the other page, but in more general, work is a definite integral. So if you want to know the work done on the object as it moves from location x1 to location x2, you take the definite integral of the force that's causing this displacement, and again, we're assuming they're lined up. And so you integrate the force from x1 to x2. Now, some problems, the displacement is not given, it's given as a function of time. Right? You can still calculate the work, and you can do it as a function of time. If I take dx, if I take the derivative of both sides here, dx equals dx by dt times dt, right? Okay, and what's dx by dt? It is velocity. So in this expression here, I'm going to replace dx with v of t times dt. And then the limits of integration get replaced. The x1 is the time that you start, x2 is the final time, and force is now a function of time. And that's the expression that we have right here. So if you know the force as a function of time, and you know the velocity, then you can calculate the work this way. Otherwise, you know the force as a function of x, and you know the displacement, then you calculate work that way. Here's the units problem just in summary. If you're working with MKS or SI units, the units of mass are kilograms, force is in newtons, distance is in meters, and work is in joules. CGS is grams, dynes, centimeters, and ergs. We're not going to do any problems in CGS. So we just have this MKS system, and then we have over here the British system. Mass is slugs, not pounds. When pounds is reported to you, the force, generally the force in which the Earth is pulling on the object, is reported to you. Distance is in feet, and then work is foot-pounds. Two systems of units, and the difference is that mass is often said is presented as though it's the mass of the object, it's the weight of the object. In the imperial system, they will give you pounds. They are giving you the force already. If you have kilograms, the mass in kilograms, then you must convert that to force by multiplying by the acceleration due to gravity. So here it is in summary. When pounds are given in a work problem, you have been given force. When kilograms are given in a work problem, you must go calculate force. To calculate force, take the mass, which is kilograms, and multiply by acceleration. If the object's being lifted, then the mass is multiplied by the acceleration due to gravity. I included some approximate densities in MKS units for several fluids. And some of the problems in the homework, you have to look into these, but I've given you the density somewhere in the written lecture notes or in this audio lecture. So you can find the density of the fluid. Sometimes I can give it to you in the homework problem. You see the variation in density. This is in MKS, and the units are kilograms per cubic meter. All right, now you have a density. If you want to get the force, you have to multiply by the acceleration, and you have to integrate. And I also gave you a chart of acceleration due to gravity within the solar system. Since in studying in this day and age, you should be prepared to go to space. And here's the acceleration due to gravity on, well, here's the moon. I only included one moon, the moon of Earth. And you can see it varies. Of course, it varies as the mass of the planet or the sun. So the bottom line from this is that work is a definite integral. When you're given kilograms, you must change the kilograms by multiplying by acceleration in order to get force. If you're given pounds, you already have force, and you can just go with it. And the two integrals that you need to know: work is the integral from position x1 to position x2 of the force that varies with displacement times dx. Work is also the integral from t1 to t2 of a time-varying force times the velocity of the object over dt.